Yeah, hi, guys. This is the first session, and I want to introduce yourself. I'm Lucas from Zopro and making the backup solution, and want to introduce, of course, our main speaker, Stefano Tempesta, Director of Engineering, lecturer and co-author at Atlas. And Stefan is a web architect working at the crossroad of Web 2.0 and 3.0 to make the internet a more accessible, meaningful, and inclusive space, as he said. Stefan is the ambassador of the AI and blockchain technology for good purposes and former advisor of the Department of Industry Australia on the National Blockchain Roadmap. He is also a technology advisor in carbon asset solution for climate action and accessibility network mission to slow carbon dioxide emission and remove excess atmospheric CO2 by using regenerative agricultural techniques and technologies. This is really hard something to understand, but I think that Stefano will show you and explain a little about the machine learning for anti-money laundering today, and about the effective solutions can help financial service fight global crime. If I miss something, Stefano, could you tell more about?
Well, that was an impressive introduction, Lucas. Thanks so much, and welcome everybody. Yes, so I've been in the technology space for a long time. Currently based in Australia, and my core field are in the application of AI technology and blockchain technology for good purposes. And these good purposes have different flavors. I look after technology for environmental impact, carbon credits, as Lucas mentioned in the introduction, and also aspects that are more connected to financial transactions, which is today's session. Today's session is about AML, anti-money laundering, basically making sure that financial transactions are used for the best purpose. I have a few slides to go through a presentation to introduce a few topics, and then I will show you how to build sort of a simple payment anomaly detection system in machine learning. A few concepts, though, to get started. First of all, I want to position not the impact of the market, the industry for AML, anti-money laundering in the industry, is a financial impact that has big numbers, dollar numbers attached to it, which are in the billions of dollars. And when I say this, it's been calculated that over $10 billion of fines has been raised to organizations that do not comply with proper regulation for AML, anti-money laundering. And also, there has been calculated that over 1% of crime across the world is connected to laundering money. So basically, to smuggle money across countries, across borders. That is significant. It's very impactful and has the impact on many people's lives. But before we go, we carry on with the solution. Let me ask you something. What is money laundering? Why is called laundering? What has anything to do with washing machines? Well, the story actually goes back at the beginning of the last century. In the early 1900s, Al Capone, you probably have heard this name in some Hollywood movies associated to some Italian mafia in the US. So Al Capone was covering his illegal business by hiding the money that he will get, that he will earn from this illegal business inside laundries that he bought all across the place where he operated. So by hiding money in this way, he will basically manage to transfer money from one place to another one without being detected. Now, eventually, Al Capone was captured and was charged with tax evasion in 22 federal states, and he was sentenced to $50,000 of death time, so it's a huge amount of money in nowadays currency, and 11 years of imprisonment. So at the end, crime doesn't pay, but it made history because now we talk about money laundering with association to what Al Capone started over 100 years ago. Now, we have historically, banks, financial institutions, been historically working with some traditional rule-based systems. These rule-based systems basically analyze a number of rules and detect whether a transaction and the individual doing the transaction is in the risk section or not. So basically, it's a sort of if-then-else, if you want to relate this to a programming language. If this transaction falls into this category, raise the risk. If it doesn't fall, lower the risk, and so on. Now, obviously, there is a big evolution since the first AML system were created dozens and dozens of years ago, which data has become more volumetric. So we have a lot of more data to analyze, and at the same time, the speed of transactions, the volume of transactions has changed a lot. This has created a problem with the traditional rule-based system. They are too slow. They can't keep up with evolving regulation, with different strategies, and with all this big data, with this complex scenario. We need something that is more automatic and can process data at scales. And you already get the idea. This is AI technology. This is machine learning. Now, very quickly, again, traditional AML systems are based on fixed rules. They raise some alerts based on these rules, and most of the times, even 95% of these alerts are false positive. A transaction seems suspicious, but it's not. How many times it happened to you that your credit card has been declined because you have done a payment for the first time in a new country because you are traveling, and then you get stopped? And then sometimes you require a multi-factor authentication. You require to receive an SMS or a code by email. But you are overseas. You're not connected to the internet. You're not roaming. So you can't receive the code. You can't unblock the transaction. It happens all the time. So these rule-based systems are really struggling with keeping up with the evolution, with the speed of transactions that happens today. Is very sequential approach. We have a lot of data, all the transactions. We organize in different rules, this rule engine, and then it comes out. Yes, suspicious, or no, suspicious, yes, suspicious, no suspicious. Often, and I'm not kidding here, there is a manual analysis of the suspicious transaction. They get listed and then analyzed by a team of people that go transaction by transaction and decide whether is acceptable or not. And this is why sometimes it takes a little bit of time for your credit card payment to be processed, or sometimes the bank even call you. How many times did it happen to you? They call you and they say, so it could be an automatic system, but they still call you and they say, we notice this transaction on this account. Is that you? Say yes after the beep, right? At least it happens to me all the time. Now, let's go more specific into AML, because the use cases that I mentioned, they're more related to payment, right? Which is connected to AML, anti-money laundering, but it's just part of it. AML is bigger than that. AML is really about also identifying victims, for example, of human crimes, as in trafficking of people, because obviously the consequences of money laundering is also in the space, of human trafficking, which is a big problem. Not very much in the media, not many people talk about it. So it obviously creates a bit of a interest in this space, because not only there is technology that can help, as we're going to see in a moment, but there is a humanitarian impact that goes beyond the financial transaction. And what I mean with this is I took a screenshot here from an application that I worked in the past, where we have identified a potential victim of a human trafficking case, gender female, age range between 20 and 30, unemployed, been with a bank between 1 to 5 years, a lot of EMT, electronic money transfers, over $100,000 in a year, receiving a lot of small transactions for multiple remitters, so from different payments. Sounds a little bit bizarre, right? So why this person is receiving such a small amount, $20 to $80, from over 200 people in a month? What kind of services is she, in this case, is female, selling? Once even received a large amount, over $900, from one male customer. And again, there is something suspicious in here, and this was triaged, escalated with the police. Now, you can understand that this where I'm going to with this situation. And it also happened in different cities, 33 different cities, 5 provinces, a lot of transportation with the like of Uber and so on. So there is something dodgy going on there, and I'm not going into defining it. You probably got the idea already, but certainly something that was identified and had to be escalated to stop this human trafficking. Now, that's the story behind it, but let's capture all the data points here. Gender, age, occupation, number of transactions, size of the transaction, number of parties involved in the transaction, geography of the transactions. All of these are data points. See, this is how anti-money laundering works on identifying all these different data points and analyzing them. There are 2 types of anti-money launderers, and they're not one or the other one. They can all both work together. Level 1 is identification of all the activities. Everything that I just said, all these data points, they are analyzed and they are checked against this rule engine. If anybody's wondering, I'm absolutely happy to share these slides after the session. So just reach out and I will definitely share this and any additional material if you're interested, obviously, to deepen your knowledge on AML and the impact that AML has on human trafficking and payment processing. Now, there is a second level of AML, which is called indirect identification. The direct identification is, let me check for all these data points. We know the data points, I just go for it and check if the conditions meet or not. Rule engine. The indirect identification is based on volume of transaction, frequency, category of transaction, where I don't know what to search for yet. Is basically a machine learning system that is looking for the principal components in data and identify these components without knowing upfront what these components are. If the rule engine works on the principle that data is known upfront, all the transaction against all these categories, the level 2 AML, so the indirect identification, works with unsupervised machine learning algorithm. An unsupervised machine learning algorithm is an algorithm that doesn't know the quality of data that it's getting. Data has not been labeled yet, and it will search for the components that qualify that data. It's a process called PCA, Principal Component Analysis, that is meant to analyze data and that is unsupervised, that is unqualified from the very beginning. Okay, now you're getting the idea. The idea is we need the machine learning, we need the AI technology to keep up with this big volume of data, especially when we don't know what kind of data we're going to get. What if we are missing something in all the transactions that we have analyzed, but those missing points are actually critical to understand whether a transaction is positive or negative. So we need to look into the next generation of AML system, which are based on knowing your customer, KYC process, that it is not just in isolation, like a siloed, where we put the customer into sort of a box and we classify, it's been screened, it's been scrutinized, and then before you get out of the box, or say that you've been labeled as high risk, then it's going to be really hard. It's like a credit score that is attached to your identity. And it goes both ways, because you may not have a negative credit score, but still perform dodgy transactions and never get detected. So we need something that has the capacity to adapt, to be more dynamic, to process massive volume of data, and also to be looking for patterns of this data that we don't know yet. Looking into something that we don't know yet is called anomaly detection. Basically, identify anomalies, something that looks different, but we don't know just yet what it is, and we have to find out. So let's get there, and then we'll jump into the system, and I'll show you how to build an anomaly detection system in machine learning. The opportunity here is to consolidate all the different data points that we have identified, profile of the client, the KYC, all the financial transactions, all your bank accounts, all your emails, anything, all the different data points, and manage them in a way that can be processed by machine learning at speed. And it sounds exciting, it is. There is a challenge though. All the financial institutions managed all this data centrally. All these big data that are used to train the model are managed by the bank, by the financial institution, and they're a little bit proprietary. They don't want to share with anybody else. Well, on one side, is understandable, right? So they don't want to share anything that is confidential information with any other institution. And as a customer, I also don't want my bank to share my data with another bank, right? So we all want that. But at the same time, you know how machine learning works. The more the data, the more accurate is the result, because models can be trained on a larger volume of data set, and obviously the accuracy can be, the precision can be increased. So basically, we need something like integrating all these different internal systems also with additional external sources that can come from third parties, from government, from other banks, and from entities, organizations that can increase the diversity of the data points that we need for analysis. Now, obviously, this is a challenge. This is a little bit of the pipeline. All the different transactional data sources aggregate across different dimensions, given as a feed to the machine algorithm, and then produce the recommendation. I'll come back into this later when we show the process in the machine learning studio environment. Now, all of these will produce a very long MEF, a model evidence framework. And again, I'm going to share this slide, so we don't have the time to go in details of all these properties or features. But what a MEF is, a model evidence framework, basically, is a categorization of all these data sources, or better, let me rephrase, is the outcome, the output of the categorization of all the different data sources. We have all the data coming from different sources, internal and external to the financial institution, and they are aggregated, transformed in a way to produce different features, looking for tax evasion, looking for inconsistency of activities, excess of expenses, unusual fund transfer, association with organizations or entities that have been identified as fraudulent in the past, lack of transparency. Like sometimes there is a transaction that is not clear where it's going and what is the purpose of it. So there are a lot of these features. Every features in the big picture of AML has a different weight. So the contribution is different. So the value is different. And there are a lot of data points. This is just one little extract of a very, very long spreadsheet that we have in the system. The purpose at the end is to define these typologies from all the different data sources that we need in AML. This process is called feature engineering, which basically means that we collect all this data and we are transforming all this data to in these risk typologies, the features that we are creating, we are engineering. Now, let me come back to the problem that I mentioned before. The problem that I mentioned before is that all these data sources, they're not just internal. If they were internal, then happy days, everything is quite confidential inside the bank. But to be able to understand, for example, geographic risk, so how a person that operates on a large geography can be identified as a smuggler, we can't rely on a local bank. The local bank will never be able to scale to different geography. And the same for the other typologies of risk identified. So we need this aggregation. This aggregation is processed with a technique in machine learning called decision tree. A decision tree is basically creating a tree structure where each data point is compared against some threshold values, and the process will go property by property or feature by feature, until all the different data points are analyzed. Now, this process obviously will inevitably expand across the different data sources, because it's going to count for transaction with unknown address in the last 30 days, foreign personal investment, country where the transaction has been executed, number of people known and unknown involved in the transaction, volume of transaction. So this decision tree is basically creating a direction into these into all these data points until arrive to the last leaf of the tree, which defines your level of risk. This is a common technique used in machine learning for analyzing data, going step by step. But again, the problem here is that these data points can come from different sources. Probably here the color coding is not clear, but the light gray are internal sources, the dark gray should have picked a better color anyway, are external sources. So in this way, there is a mix of internal and external sources. And mixing different data sources creates always a problem of data privacy and data leakage if put in the wrong hands. So we need to move into an aspect of confidentiality, which is actually called confidential AML, confidential anti-money laundering, which basically leverage trusted execution environment for allowing multiple financial institutions, multiple banks, to share in a confidential way their data sources. The machine learning algorithm runs inside this trusted execution environment, which is agreed between all the different banks. Data is encrypted, and the machine learning algorithm is able to process this encrypted data without any transformation and without disclosing this data to the other banks. So the original data set remains in the hands of each bank. An encrypted copy of it is shared with the other institutes, and obviously the algorithm will benefit from this larger volume. This technology is called confidential computing and is an addition to the traditional encryption technique that we already know. We know how to protect data at rest when it's stored in a database, for example. We know how to protect data when it's transferred to over the wire or over the internet, HTTPS, for example. This technology is the new way of encrypting data when it is in memory, in use, because in that moment, the data is accessible, is visible. And it basically works by reserving a space of memory in the virtual machine, in the container where it is running, so that the data and also the algorithm of the machine learning app, the code itself, runs in complete isolation. This isolation is done by the CPU, so is hardware encryption. The hardware, the CPU, creates a protected enclaves where the code and data runs and the operating system cannot access. The hypervisor cannot access. So this prevent access even by the cloud hosting provider. So if you run this in AWS, in Azure, in the Google Cloud, wherever you run it, no one at Amazon, at Microsoft, at Google can access your coded data because they are protected inside a hardware secure enclaves. Now, this was just an extension to my conversation. Let's go back to machine learning and the anomaly detection. So this is where it gets important. It gets important because now we know that we can aggregate different data sources from different sources. We can data set from different sources. We can confidentially process to analyze and to engineer all the different features. And we can now build the machine learning algorithm. So I'm going to show you this here. You can see, yes, you can. I'm running a machine learning studio. There are there is a classic and a modern version. I'm still on the classic one. I haven't moved to the modern side, but I will. I promise I will. For now, it's okay to work on the classic version. Here, we can create what are called experiments. An experiment in machine learning terminology is an algorithm that starts with data and produce an output, which is a score. Okay, so I have created here, and now I'm going to look into my second screen here. So here we go. Payment anomaly detection experiment, and is a predictive version. Okay, so let's start with the regular experiment. This regular experiment is built by defining a flow of action. We start with the payment data, which I'm going to show you in a moment. Obviously, is a sample data. I simplified this data, extracted from a larger data set. I have removed a lot of confidential data. Yes, there are some names of people that have been made up. So everything here is meant to be used for the purpose of this demonstration. In the real world, you will have thousands and thousands and thousands, even millions of rows and hundreds of different columns. Again, here I have simplified, and I'm picking only the timestamp, the name of the person, the description of where the transaction was done. They bought something on Amazon, the country, and the amount they spent. Okay, obviously there can be a lot of other features in there, a lot of other columns. And if you look into, for example, identifying a client and comparing with the amount they spent, then we can see this nice diagram here, which is a multi-box plot, which basically is telling me that for each client, Johnny, Brian, Mike, Jill, they have spent from a minimum to a maximum, but the majority of the transaction is in this box here. In the case of John, between just a little bit less than 80 euros and a little bit more than 160 euros. And the average is the line in between 120. Mike, instead, is in between 80 and 100. So let's say it's about 90 and 220 with an average of 150. Okay. So in this way, we start identifying how people are spending their money. Now, after this, we're going to go into the training. You know the process of machine learning, right? So you load the data set, you split the data between a portion of data that is used for training and another one that is used for testing and the algorithm. So this split data does exactly this. Split the original data set in a number of rows that are used for the training. So then the algorithm can be trained against that data. And the other ones, the other lines, the other rows are used for the actual testing of the train model. So for training, we are using an anomaly detection. This is what we are doing, right? So we want to identify anomalies in payment patterns of these people here. And we use a one-class support vector. Now, I'm not a data scientist. I'm an engineer. I build this stuff, but I don't write the machine learning algorithm to create this one-class support vector machine. But basically is a technique for machine learning anomaly detection. There are different other techniques that can be used. In this case, the one class basically is a similar concept to the decision tree that we have seen in the previous slide, where there is a classification of data where there is one type of the other one, in this case, where there is a risk or not. Now, it goes all the way until the scoring, and the scoring at the end, we can also display the score data set, identifies a score probability, and the probability is a number, obviously, that identifies the likelihood that a record is in the range of in the detected range or outside the detected range, and therefore an anomaly. How do we do this? Now, the good things about this machine learning studio is that you can just set up a web service. Basically, after you write all your algorithm, click the button and publish as a web service, completely hosted in the cloud. You don't have to provision any virtual machine. You don't have to provision any containers and no web server. There is no coding. There is no Node.js. There is no Python. I mean, if you want to, you can add some Python modules or even R, which is not the programming languages of data scientists, but you don't have to. There are many machine learning algorithms ready to use for anomaly detection, classification, clustering, regression, and so on, so on, so on. Maybe this can be a topic for another session, another time. Now, stay in this here. We're going to go into the experiment that has been published as a web service. I open my web service, and this web service can be accessed in any programming language that can do an HTTP request. Right? So if you can see now here, it's going to open the post URL with the authentication bearer that you have to put inside, and the request, which is a JSON payload where you pass these parameters, and the response, which is another JSON file that contains the score probability. Now, instead of looking into this JSON file, we can even test it directly here. So we can test directly how algorithm performs on the spot. So we can say today is 21st, yes, 21st of May, 2024. Our client, Mike Randall, has spent on Amazon in Ireland 100 euros. Okay, so we can test the response. And based on the trained model, we get this score probability, which is very low, but is an indication of the distance of this transaction from the center, from the anomaly range. Okay, obviously higher number, it means that the probability is higher. So if I increase the transaction and go to 1,000, not much happens for this guy. Let's change country. Let's put him in Australia. And yes, so there is a change of value here. So obviously, changing conditions create different ways of testing data that at the end will produce these figures that was in the picture before. If I manage to get back with my mouse, I can show that again. This one here. So all the transactions are within a range of typical activities. Those that are outside, because the number is of the score probability is different from the average, then they are possible fraud. Now, obviously, this is one type of anomaly detection, purely for payment. But as we understood, there are many anti-money laundering solution. So an AML solution is a collection of several algorithms. Each of them is processed. Each of them raise an alert, and each of them is analyzed for producing the final result. And I would say, just last slide, say after implementing this AI-powered AML system, we measure an increase in the overall performance of the system. Well, this is what we expected, right? So a reduction of 85% of false positive alerts and an increase of over 200% of money laundering activities. So thank you very much for your attention. We have a few minutes for some Q&A. I know there is a lot of information in here.
Yeah.
The idea is certainly to not trigger your interest. And obviously, if you want to know more about it, feel free to reach out anytime. Lucas, over to you.
Yeah, thank you. Thank you for your presentation. Really good. But maybe I want to have only ask you about something.
Sure.
Because I am always thinking about the security and trying to find the way if those data, those systems are separate if the clients want, because you tell that you learn the system for private data or global data, right? And
correct.
If some clients want to have only private, I think you may to have the private things, right?
That's correct, yes. So to make an AML system work at its best, you need to have a combination of private and so internal and external data sources. And you need to protect these data sources by preventing sharing. I described one technique, which is called confidential computing. There are a few other ones that are used. Most organizations simply encrypt data with asymmetric encryption, which is a good way of doing. The only challenge is that then you need to protect your keys as well. So if your keys are compromised, then obviously your encryption is compromised as well. With confidential computing, instead, encryption is at hardware level. So the encryption key is in the CPU. The only way to compromise a trusted execution environment is to compromise the hardware.
All right. Thank you. Thank you. Now we're waiting maybe a few seconds for another questions. If you have some, then place us on the chat, and I will show the all those questions on the screen, guys. And maybe before we decide to finish, I want to ask you about how long it takes the learning process.
Yeah, good question. It is typically hours. It depends obviously on the volume of data and the number of data points that are analyzed and the volume of transactions. These algorithms take hours and hours to complete the training. And I believe when we ran it for the first time, it took like 12 hours or something. But then the beauty of it is that you don't need to do a full training all the time. You do an incremental retraining with a new transaction that come. The retraining still takes time though, because every day there are transactions, right? So it's not something that changes once in a while, like every week or every month. Every day you have new transactions. So every day there is a retraining process in place. So this is why it's also important to set up your cloud infrastructure properly. The infrastructure for training and retraining has to be quite robust, possibly even using GPUs that are more powerful for this numeric calculation. And instead, the infrastructure for the scoring, so which is the prediction based on the trained model, can be a bit lighter because you don't need a lot of computing power for the scoring mechanism.
Cool. That's cool.
So yeah, consider AML also from a microservice perspective. We have
that was my next question. That's right.
The other one for scoring, absolutely. Yeah.
Yeah, because the clients, if the clients want to send the new data, then they always open it for right over the some API or okay.
Exactly right. Yes. Yeah. Well,
any questions, guys? I think we may to even close to finish, and if you don't have any ideas, want to say more, because the time is almost finishing. Got 1 minute. If anybody wants to ask about something, 3, 2, 1, no one. Okay.
That's right. Yes. Glad to be here. Enjoy the conference. This is a great event. It's my second time, and look forward one day to meet everybody in person. Have a good day.
Yeah.
Bye, everybody.
Thank you very much. Bye-bye, guys. Thanks.